Again, thanks for the opportunity. And it's interesting. We were talking about regional scale and then structural scale, now down to molecular scale again. I try to kind of share with you, how you potentially could use the magic of chemistry to change things at very fine scale and have much larger implications, I guess. So here, the talk is about durability of CFRP-wrapped concrete in cold regions, a lab evaluation of montmorilloite, nanoclay-siloxane epoxy adhesive. This actually links well with the talk we just heard from Simpson-Strontai. Again, this one focuses on the interface, especially the adhesive. So my collaborators include Mr. Zhipeng Li, one of my PhD students, and also one of the visiting scholars to my group, Dr. Zhen Lei. So again, the outline, start from introduction, then experimental program, results in discussion, conclusions, and future work, and with acknowledgement. And these look very familiar because I use the same figures or photos for the prior talk. Basically, again, we're seeing more and more reliance on chloride salts for better winter mobility and safety. And there are some unintended consequences when it comes to concrete durability. And the most recent knowledge we have is the presence of salt not only accelerate or increase the risk of physical damage, but also induce chemical attack. So basically, you are seeing calcium leaching out of the concrete or the CSH gel, and the formation of some expansive crystalline faces inside the concrete, which can cause cracking and increase permeability. So one of the tools in the toolbox is the externally bonded FRP fabric. And well, again, you can see this photo was adopted from Simpson-Strontai, sort of illustrate how we use FRP after seismic damage or for the need of repair, retrofit, or strengthening. However, there's a lack of research on how to address some of the weaknesses for this, what I consider as FRP concrete composite material, to improve their durability performance in aggressive environments. For instance, the concrete could be subject to dual or even multiple distresses. Like in the case of salt scaling, we're not only looking at free salt damage, but also chemical attack. There is a need to prevent or minimize the ingress of water. Like we mentioned earlier, if we can keep the water out, we can keep the chlorides out, we can keep the sulfate out, the concrete will be lasting a longer time. So the interesting thing is, over the years, as you can see the photo at the very bottom right, the United States has getting more and more addicted to road salts. So this increased usage of road salts, there are a lot of unintended consequences, one of which is the durability of our concrete infrastructure. So again, with nanoengineering, we probably could make a little difference or significant difference. So our thought process was, okay, instead of trying to densify the aged concrete, we might be better off relying on the FRP and enhance one of the weakest links in the FRP, which is the adhesive. I think Alex earlier kind of implied, yeah, there may be some challenge with the UV aging unless you put a coating, top coat on top of the FRP, but arguably the adhesive usually are epoxy resins. They are not only vulnerable to UV aging, but also to water. When exposed to wet-dry cycling, the epoxy can get more and more brittle and eventually crack. So we know already that nano modification could endow epoxy resin with better performance. There's lots of studies out there. For instance, using nanosilica or carbon nanotubes or nanoclay, nano titanium to give epoxy higher cross-linking density, or sometimes we're seeing better mechanical performance in terms of improved hardness, modular, toughness, strength, and so on. Now, in terms of durability, what's highly desirable is, again, nanoclay is a 2D nanomaterial, so it gives better barrier performance of the coating layer or the adhesive layer, and also better thermal properties and better adhesive strength. And also, when it comes to FRP concrete composite materials, so far the studies I've seen only, I mean, at least in the published domain, is only carbon nanotubes. And as you know, these materials are very expensive. So how about more affordable nanomaterials? So we go back to the sodium montmorilloite nanoclay, and this is a 2D material with the lateral size about 20 to 25 microns, but the thickness is a few nanometers. And this material hasn't been evaluated for possible modification of the epoxy adhesive in FRP concrete applications. So our hypothesis is that by incorporating a small dosage of nanoclay into the epoxy adhesive, that would significantly improve the properties of adhesive and therefore enhance the performance, mechanical durability and mechanical properties and durability performance of the externally bonded FRP to concrete. So for that purpose, we fabricated 5 groups of concrete specimens or cylinders in the lab. One is reference concrete without any FRP. One is FRP-wrapped. The other one is nanoclay modified FRP-wrapped. And then the last 2 groups, we first age this concrete and then wrap it with FRP with or without nanoclay modification. So the idea is that the nanoclay modification not only would benefit the FRP used for new structures, but also for aged structures. So here's the mixed design. As you can see, the water cement ratio of this concrete is 0.33, and it's a 2x4 inch small cylinders cured in the lab. And then the pre-aging was done through exposure to 175 rapid freeze-thaw cycles in 3% sodium chloride. And we are achieving approximately 15% reduction in compressive strength. And then we call that a different group, which is a pre-aged concrete group. So for dispersion, again, we're looking at about 1.5% by weight of the final epoxy adhesive and using ultrasonic dispersion. And for wrapping the FRP to the concrete cylinders, this is dealing with 2 different groups, right? One is the new or reference one, the new concrete or the pre-aged ones. So for both groups, we start oven drying them to remove residual moisture. And then for the pre-aged one, sometimes you have significant scaling due to that salt scaling exposure. So we had to smooth some of the surface with a very low quality mortar, I would say, water cement ratio of 0.5, just so that your FRP would bond better. And then spray this adhesive at this dosage recommended by the vendor before wrapping the FRP and cure it for 7 days. So again, a number of tests were run. Some were compressive strength salt scaling tests, and the more mechanistic ones include water absorption, gas permeability, and water contact angle. And then to shed more light on the issue, we also used optical microscope, thermogravimetric analysis, differential scanning calorimetry, and Fourier transformation infrared spectroscopy. So for the water absorption test, the cylinders were basically cut in the middle to get discs, and then only the sides were not sealed, so that we want to see how water penetrates through that interface between the FRP and the concrete. And for gas permeability, the same deal. We're mostly looking at that interface. So salt scaling test, the cylinders were exposed to this accelerated wet, dry, freeze-thaw cycles. You can see for each cycle, it's about 6 hours, but the freezing duration is approximately 4.2 hours. In other words, the other times of the cycle, the post-solution is not frozen based on our estimate, knowing that the freezing point temperature of the 3% sodium chloride is about minus 1.8 degrees Celsius. And the freezing rate is also important. As we know, this is an accelerated test. In the real environment, in the field, you probably won't be seeing as fast freezing rate. Therefore, your concrete should last much longer. Now, starting from compressive strength, one interesting thing is that once we confine the cylinders with FRP, of course, in this case, we are seeing increase in compressive strength because of confinement. It's about 99% or 82% improvement by the FRP for the new and pre-aged concrete respectively. And then after salt scaling, the 1.5% nanoclay really benefit the strength of both the new concrete wrapped by FRP and the pre-aged one. The benefit was 6% and 39% at 200 freeze-thaw cycles respectively. And now once you further expose it to more freeze-thaw cycles, then the benefit of nanoclay is even more pronounced. Well, part of the reason is when we look at the cured epoxy adhesive under the microscope, you'll see A is the one nanomodified, which is very dense and crack-free, and B is the one without nanomodification, and it's not as homogeneous and it has some macro cracks. So what about failure mode of these small cylinders wrapped in FRP? You can see we observed several different failure modes. One is crushing, relatively homogeneous, which is figure A. Figure B, you are seeing some eccentric compression. So this crushing, and on the other side, you have some tension-induced cracking. And figure C shows a third mode of failure, which is rupture of the FRP fabric. And figure D shows the very last failure mode, which is debonding of the FRP. Usually you see that with the pre-aged concrete, which is much weaker, and after many freeze-thaw cycles, so the concrete was really compromised. So in terms of mass loss, you can see on the left-hand side, after 200 freeze-thaw cycles, the control group without FRP, you're seeing more than 55% mass loss. However, when you have FRP, whether it's nanomodified or not, you're seeing much less mass loss, so less than 20% after 400 cycles. Now, it's interesting because the FRP fabric wrapped around the cylinders, concrete cylinders, and each end we have about 5 centimeter or 2-inch additional protection, but overall the top and the bottom were not protected by FRP. So over time, you're seeing this change in length diameter ratio. Of course, for the reference one without, the black dots without any FRP, that change is minimum because their deterioration or scaling is somewhat uniform on all sides. But for the FRP ones, because you're most seeing scaling on the top and the bottom, therefore you're seeing length to diameter ratio keep changing. So here are some of the digital photos, after a different number of freeze-thaw cycles on the left, which is not protected by any FRP. On the right-hand side, like I said, it's mostly scaling on the surface, exposed surface. Now, the incorporation of nanoclay benefits the performance of this FRP concrete composite. First of all, the modulus, elastic modulus on the left, you can see that after the FRP protection, you're seeing some benefits, for both the pre-aged group, which is the solid line, and the new concrete group, which is the dashed line. And in terms of gas permeability or gas impermeability, you can see that compared with their non-modified counterpart, with nanomodification, the 0 cycle number of cycles, which is prior to salt scaling, or 325 freeze-thaw cycles, or 200 freeze-thaw cycles for the pre-aged one, all of them show that the gas permeability or gas loss is less. So therefore, in other words, they preserved a little bit more gas impermeability because of the nanoclay. So the benefits are about 26% or 16%, depending on whether it's a new concrete or pre-aged concrete. Again, this is due to this denser microstructure and more crack-free microstructure, keeping the CO2, oxygen, and moisture vapor outside. Now, the nanoclay also slow down the water absorption. On the top is the reference group without any FRP. The reference group, which are on, I should call it a new concrete group, and the bottom is the pre-aged group. On the right hand side is just the the first initial stage of the absorption. Basically, the surface area under each curve is the amount of water absorbed during that time. Of course, the reference one is the black one at the very top, so that absorbs the most water. In other words, for both the new and pre-aged group, once you have FRP or nanoclay, either way, they're reducing the amount of water incorporated, and also they're slowing down the water ingress. So you can see the difference. Now, if we measure the quantitative initial water absorption, which is the first stage on that curve, corresponding to how fast moisture is moving into the microcracks and the pores, you can see in some cases, especially for the pre-aged group, you are seeing 77% reduction, which is highly desirable for the durability of the concrete. And even for the new ones, you're looking at 30% reduction by this 1.5% nanoclay. However, if you look at the secondary water absorptivity, there's no significant difference because that's more how fast you fill up the air voids. So again, mostly we're dealing with the microstructure and a little bit improvement on the water, on the hydrophobicity. However, they're still hydrophilic because one is about 43 degrees. The other one after nanomodification is about 54 degrees. So still both of them are hydrophilic, but the nanomodification did reduce the surface free energy slightly. To further improve the hydrophobicity, what really needed is a synergistic effect with another type of nanomaterial or higher dosage of the nanoclay. So you have some micro assembly. Again, back to that lotus effect. Now, also we look at the interrelationship between some of these parameters. As you can see, the pre-aged group seem to, these are orange dots, seem to follow a different trend than the new group. But both of them, the trend is such that the higher water absorption coefficient, meaning that they're more compromised in microstructure, than they have lower strength and lower modulus. Now, in other words, the strength and modulus at the bottom left shows that they follow almost a linear one-to-one relationship. So the higher strength, higher modulus, and less compromised microstructure. Same thing on the right, bottom right, the higher water absorption coefficient corresponded to higher gas permeability and more compromised microstructure. However, the orange dots are not showing a very clear trend because remember, these are the pre-aged cylinders. We had to use a mortar to smooth the surface, which made this gas permeability probably less reliable. Now, also the nanoclay reduced the crack width of some of the composite materials, especially the one in the middle, B versus C. B versus E. E is modified for new concrete after 325 number of freeze-thaw cycles. The crack width is much reduced than the one without nanomodification. However, when it comes to pre-aged, the benefit of nanoclay to reducing the crack width was not significant. And also the Fourier transformation infrared spectroscopy confirmed the nanoclay chemically reacted with the siloxane epoxy resin. And the nanoclay also increased the glass transition temperature and improved the thermal stability of this epoxy. For instance, the glass transition temperature increased from about 48.5 degrees Celsius to 50 degrees. And this phase transition also from which we were able to calculate the thermal energy So there's a difference between 0.248 to 0.294 joule per gram degree. So that indicates a higher cross-linking density, which agrees well with the previous literature, even though they were mostly using the epoxy for a coating, not for FRP adhesive. So to conclude, this work demonstrates the beneficial effect of 1.5% nanoclay modification to the protective performance of externally bonded CFRP. And basically the results showed better mechanical performance after salt scaling in terms of elastic modulus and compressive strength. And also the nanoclay was able to slow down the ingress of water. The benefit was especially pronounced for pre-aged concrete. And the reason is that this improved microstructure and surface properties of cured epoxy, resulting in lower water absorption and lower gas permeability. And also the nanoclay had additional benefits in thermal stability and higher glass transition temperature. In terms of future work, we envision that there could be other adhesives or other nanomaterials or more than one type of nanomaterial to be investigated. And in addition to salt scaling, one could look into other surface environments in terms of sulfate, acid, or microbes, or UV aging. And again, starting from molecule level to materials level to structural level testing. I'd like to thank my collaborator, Dr. Lei, and his funding was provided by China Scholarship Council and Yunnan University. And my team's funding was from Tridley. And also we thank Simpson Strong Tie Premix Company, BASF Company for donating the materials, and Mr. Xiang Zhang for helping with the software and visualization. And the work has been published in Construction and Building Materials recently. Thank you, and I'd like to take your questions.
Stuff, I have one.
Sure. Yeah, I just wanted to thank him. Yes, please go ahead.
Well, yeah, go ahead and thank him. I can thank him. That was really fascinating. I wish, Xianming, you had done this work when I was working on bridges many years ago. Anyway, I'll send you the papers. We've done some durability studies, and we found out the age of the concrete is very important with FRP. And of course, we had some specimens on the bridge, and we had some specimens in the lab. And the difference was significant between the two, because in the bridge, you have much more serious condition. Like 3 times, we could see that, yeah, we had the strength capacity reduced 3 times. Now, it wasn't much, it was like 9%, but that was 3 times what we saw in the lab.
Yeah, again, probably back to the UV aging and moisture damage of the cured epoxy.
Yes. I think that was a major thing. Anyway, I sent you the papers, and my question, of course, is, can the companies like Simpson Strong Tie, can they do this modification with minimal cost?
I do think so. Yeah. Again, depending on how far you want to go or what's your intended service environment and application, a lot could be done. Yeah, it could be something very simple. It could be more sophisticated, like I mentioned, more than one type of nanomaterial. But because the nanoclay is the cheapest one.
Right, they already put 1 layer of epoxy on the concrete before they wrap the wet carbon fiber. So that first layer could have the nano modified properties, and then the problem is solved. Thank you.
Well, the nanomodification will probably increase viscosity, so you have to play with the workability a little bit.
Yeah, but I think these are problems that can be solved.
Right. Those are easy ones. And also in the past, I've also used nanoclay to modify epoxy coating. And this adhesive strength could, in some cases, increase significantly, like double, for instance.
Okay, thank you.